So I'm now going to talk about gradient descent. So gradient descent is the way to get to the minimum or even the maximum of a function by following the gradient and iteratively moving down along in the appropriate direction. And this is a very useful technique because we can use this to minimize the error in matching how well a particular system fits some data. And this is particularly the case with neural networks and linear regression. We'll go through those examples. The idea really is as follows. We're going to talk about ascent now just because we're going to climb to the top of a mountain, but it's just the same kind of principle except we're going up, not down. How do we get to the top of a hill? Well, if we are looking locally at what we're doing, what we do is we look at the path we're on, and if we want to get to the top, we want to make sure that we're walking uphill. So you'd want to look around and make sure that we're actually walking in the direction where the gradient points upwards. Again, if we want to get to the bottom, we do the opposite. We look at the path and say, is the path leading downwards? Has it got a steep downwards gradient? And if we want to get to the bottom, we just carry on going in the direction of the gradient. And if you want to get there as fast as we can, you'd go by the steepest path. Right, follow the gradient. How do we know we're at the top? Well, if you're at the top of a hill, everything goes down on both sides. Same thing is true for mathematical functions. We can also say, when things are gradients, we can see when things are maxima and minimum on mathematical functions by consideration to the gradient. When we're actually at a peak or at a minimum, then the gradient's going to be 0, and pointing towards it, the gradient's going to be going up, for example, to a maximum. And like I said, this is a useful technique as well because what we can do is we can also design models, right, mathematical models of data, and we see how well they fit the data, and we've got parameters we have to adjust. And what we do is we do gradient descent in parameter space in order to get a good fit. And we'll come into that in a lot more detail in the next few lectures. So here we're just pointing out a few important points on this particular quadratic bowl-shaped graph, in fact, x along the bottom and y at the top. In this particular location here, we see that we've got a negative gradient, so dy dx, change in y divided by change in x is negative. So if we wanted to get to the bottom, we'd follow all the way down here. At the bottom, basically the gradient goes to 0 because it's actually, you're not going up or down at the actual minimum point. It's actually a 0 gradient. And if we start moving up a bit further again, we see now we have another gradient which is non-zero. In this case, dy dx is actually positive. We can also draw a tangent on a graph at a gradient point as well. So here we have a graph. This is y equals x squared, as it turns out. At that particular point there, let's draw in a tangent which just touches at that point. And the gradient of the tangent is, of course, the gradient of that point on the curve. Now, because it's a straight line that we're drawing on for the tangent, we can then look at, over a large period or a large distance, what the change of x is and the change of y is, and get a fairly good estimate, in that case, of what the gradient of the tangent to that point is. So basically for a straight line, the gradient is quite easy to calculate. It's basically going to be the ratio of a small change in x, or a change in x divided by a change in y. And in fact, it doesn't actually have to be a small change in x or a small change in y for a straight line, because it's not something which is only defined at the point. The whole line has that gradient. So we just have to measure a change in x and look at the corresponding change in y and calculate the ratio. So for example, here's 2 points that go through a straight line, 2, 3, and 6, 5. So the change in y is going to be 5 take away 3, which is 2. The change in x is going to be 6 take away, so 5 take away 3, which is 2. And the change in x is going to be 6 minus 2, which is 4. So the gradient is going to be change in y divided by change in x. 2 over 4 equals 0.5. So again, like I said, sometimes we want to find minima. Sometimes there's going to be global minima and local minima, and global maxima and local maxima as well. So this is one of the issues that we have to consider when we're actually minimizing real functions in the real world. It could be that we can use gradient descent, but what might happen is we might get stuck somewhere local. So here's a global minimum in this particular accept of this function that we can see, but here's a local minimum. So imagine we started off doing an optimization and we're trying to follow the gradient to find the minimum, and we start at this point. We might end up going down here, and then we get to this point here, this local minimum, and we can't go down any further because we're now in a local minimum and stuck there. Similarly, here's a local maximum. If we were trying to find the maximum and we started, say, here, we might end up going up there and then finding this maximum, but it's only a local maximum. In this particular except, you can see there is actually also a global maximum as well. So that's a problem that we have to deal with when we're minimizing or maximizing functions by gradient descent. We have to worry about whether or not we're stuck at a local minimum or a local maximum. And really one way to get out of that is to try lots of times from lots of different random starting positions. And that's exactly the same thing that you have to do with neural networks. So what we need to do then is to be mathematically rigorous. We have to see really if something is a maximum or a minimum or a saddle point. And we can do that, not a saddle pint. We can do that by examining the gradient on either side. So a local maximum will have basically the gradient such that we go down from either point. Local minimum, we're going up from either point when we move around from that point. But a saddle point also has a zero gradient, right? It's got a zero gradient, but it's not actually a minimum or maximum. But you see the change in the sign between before and after. So if we want to be rigorous about these things, we want to check just slightly around these points as well to check that they really were local minima or local maxima, or in fact just simply saddle points. We won't really have to worry about that at all when the kind of functions we're actually minimizing, because we're going to be minimizing quadratic terms, and there really will be a nice well-defined minimum most of the time and not a saddle point. So then the minima and the maxima, we know that the gradient's going to be 0. If we were doing this analytically, so if we had a function, mathematical function, and we wanted to find the minimum, what we do is we differentiate the function with respect to the other variable, and then we'd basically set the gradient to 0 and solve the equation. And that's something else we can do with our gradient, with our minimization. If we've got a closed form solution to something, what we can do is we treat it like a mathematical function. We can also differentiate this and set it to 0 and then solve the equation. And in simple cases, certainly linear equations, we can actually, linear equations or simple equations with quadratics, we can actually solve them and immediately say, how do we find the minimum, right? And we don't necessarily have to use iterative methods. So iterative methods would look something like this, right? That we start somewhere randomly. In this case, let's say it started here, and then we just move down the gradient in order to find the minimum. So you jump a little tiny bit, and then you look again at the gradient and you say, yes, it's got to go down a bit further. So we jump a little bit further down, and a bit further down, and a bit further down, and then the gradient starts getting smaller and smaller. So if we're doing gradient descent by an amount relating to the gradient, we get smaller and smaller and smaller and smaller steps until we get to the bottom and we're hardly moving at all if you use a naive technique, and it converges to this local minimum. Okay, move down until we find it.